Hello everyone, I am Dr. VRAO. In the last video, we had gone through the concept overview of solubility product and common ion effect. In this video, we shall solve some problems based on the solubility product and common ion effect, because these two concepts are interrelated and questions are always being asked in the combination of these two concepts. Let us do some problems, right? Okay. Problem 1 is a solution which is 10 power minus 3 molar each in Mn plus 2, Fe plus 2, Zn plus 2 and Hg plus 2 is treated with 10 power minus 6 molar sulphide ion. If Ksp of manganese sulphide, iron sulphide, zinc sulphide, mercury sulphide are 10 power minus 15, 10 power minus 23, 10 power minus 20 and 10 power minus 54 respectively, then which one will precipitate first? Okay. So, to solve this problem, already I told you precipitation takes place when ionic product is greater than solubility product. When ionic product is greater than solubility product, precipitation takes place. Ionic product is greater than solubility product, then precipitation takes place. So, let us calculate the ionic product. They gave that solubility products of MNS, FES, ZNS, HGS, but they did not give the ionic product values, but we can calculate the ionic product values with the help of given data. Okay. So, let us write these MNS, FES, ZNS, HGS, right. And these are the given data: manganese sulphide, iron sulphide, zinc sulphide, mercury sulphide, in which each ion concentration is 10 power minus 3. They gave that each ion concentration is 10 power minus 3 each in Mn plus 2. They given that each ion concentration is 10 power minus 3 and each ion is treated with 10 power minus 6 molar sulphide ion. So, if MNS, the Mn plus ion concentration is 10 power minus 3 and it is treated with 10 power minus 6 sulphide ion, then ionic product of manganese sulphide is concentration of Mn plus 2 into concentration of sulphide ion S minus 2. So, S minus 2 is 10 power minus 6. Okay. Mn plus 2 concentration is 10 power minus 3 and sulphide S minus 2 ion is 10 power minus 6. Then ionic product is 10 power minus 3 into 10 power minus 6, which gives 10 power minus 9. So, we can get the ionic product of each ion is 10 power minus 9. Each ion is 10 power minus 9, right. 10 power minus 9. Okay. So, each ion concentration is 10, sulphide ion concentration is 10 power minus 16, minus 16, then it 10 power minus 19. So, ionic product, we can write the ionic product values here and Ksp, solubility product values here. For manganese sulphide, ionic product which comes out to be 10 power minus 19, which 10 power minus 19, because concentration of Mn plus 2 is 10 power minus 3 and sulphide ion concentration is 10 power minus 16. So, ionic product is 10 power minus 9. 19. So, manganese sulphide solubility product is 10 power minus 15, 10 power minus 15, and ionic product of each salt, that is this is also 10 power minus 19, this is also 10 power minus 19, and this is also 10 power minus 19, because each ion concentration is 10 power minus 3 and sulphide ion concentration is 10 power minus 16, right. Okay. So, ionic product values are these, and they gave that solubility product values, that is for MNS 10 power minus 15, for FES it is 10 power minus 23, and for ZNS it is 10 power minus 20, and for HGS it is 10 power minus 54. Then they asked to they asked to calculate which one will precipitate first, which one will precipitate first. So, in order to precipitation, this there should be one condition holds good, that is ionic product is greater than solubility product. In such case, precipitation takes place. Let us compare the ionic products and solubility products. 10 power minus 19 is ionic product and solubility product is 10 power minus 15. So, in this solubility product is greater than ionic product. So, in this case precipitation do not takes place, and in this case ionic product is greater than 10 power minus 19 is greater than 10 power minus 23, but in this case precipitation takes place, in this case precipitation takes place. And in the case of Zn sulphide, zinc sulphide, ionic product is 10 power minus 19 and solubility product is 10 power minus 20. So, ionic product is greater than solubility product. So, in this case also precipitation takes place. Okay. So, and in the mercury sulphide 10 power minus 19 is the ionic product and 10 to the power minus 54 is the solubility product. So, ionic product also greater than solubility product in this, but they asked to clarify they asked to calculate the which one will precipitate first, which one will precipitate first. Then there is a formula, the ion with the least solubility, precipitates first. So, in these three ions, in these three solubility products, solubility is very less in the case of HGS. So, HGS precipitate first, then precipitation takes place in ZNS and FES. So, precipitation takes place in HGS because the ion with the least solubility will precipitate first, right. Now, we shall go for second problem. Okay. And the problem 2 is, if Ksp of Ag2CO3 is 8 into 10 power minus 12, the molar solubility of Ag2CO3 in 0.1 molar AgNO3 is. So, they asked to calculate the molar solubility and they gave that solubility product of Ag2CO3. So, Ag2CO3 we have to write ionization, that is equilibrium. Ag2CO3, it dissociates as 2Ag plus 3 plus CO3 2 minus, CO3 2 minus. Okay, sorry. Solubility product of Ag2CO3 is 8 into 10 power minus 12 and the molar solubility of Ag2CO3 in 0.1 molar AgNO3 is. Okay, so Ag2CO3, in this case we have to write the equilibrium, that is Ag2CO3 dissociates as 2Ag plus CO3 2 minus, okay, CO3 2 minus. So solubility product, they given that the solubility product, so we can write the solubility product. So concentration of Ag plus whole square into concentration of CO3 minus 2. Okay, at equilibrium whose concentrations are 2s and s, whose concentrations are 2s and s at equilibrium. Okay, so we can substitute that concentration. So 2s whole square plus 2s whole square into concentration of equilibrium concentration is S. But they asked to calculate the molar solubility. This molar solubility in 0.1 molar AgNO3, in 0.1 molar AgNO3. This is the case of a common ion effect, because in AgNO3 Ag plus is there and in Ag2CO3 Ag is there. So there is a common ion present here. So they asked to calculate the molar solubility of Ag2CO3 in 0.1 molar AgNO3. So let us take the Ag2CO3 solution in AgNO3 solution. In 0.1 AgNO3 solution, in addition to these concentrations, common ion concentration also adds. That is, Ksp is equal to 2s. 2s is the concentration, okay, molar solubility of Ag2CO3 alone. But in 0.1 AgNO3, 0.1 molar concentration of Ag adds to Ag plus of Ag2CO3. So this much amount adds. So because we are adding 0.1 molar AgNO3 solution to Ag2CO3, that is, we are increasing Ag plus common ion concentration, right? So 2s in plus 0.1, no, yes, right? So, and you know one thing, when common ion effect is there, solubility decreases, and degree of dissociation suppresses. Okay, so we can neglect the molar solubility of Ag2CO3, molar solubility of Ag2CO3 in the presence of 0.1 molar AgNO3, because common ion effect, and solubility product is very less, 8 into 10 power minus 12, right? So we can neglect the 0.1 is more, common ion concentration 0.1 is more than 2s. So we can, when compared with the molar solubility of Ag2CO3, we can neglect the 2s, right? So 0.1 whole square, and they gave that solubility product, 8 into 10 power minus 12, right? So in the next step, 8 into 10 power minus 12 is equal to 0.01 into 0.1 whole square means 1 by 10 square, 1 by 100, 0.1 means 1 by 10 whole square. So this which comes out to be 1 by 100, and 1 by 100 is 0.01. So right, next, and in this step, next step, S is equal to 8 into 10 power minus 12 by 0.01. 8 into 0.01 means 8 into 10 power minus 12, 0.01 means 1 by 100. So this 100 goes up, then S is equal to 8 into 10 power minus 12 into 10 square. So, S is equal to 8 into 10 power minus 10. So, molar solubility in 0.1 AgNO3 is 8 into 10 power minus 10. Okay, this is the example for common ion effect. Okay, here Ag and here Ag are these two. This is the case with the common ion effect, right? Next problem. Okay, problem 3 is the molar solubility of cadmium hydroxide is 1.8 into 10 power minus 5 molar in water. The expected solubility of cadmium hydroxide in a buffer solution of pH 12 is, right. They asked to calculate the molar solubility of cadmium hydroxide in a buffer solution of pH 12. Okay, in a buffer solution of pH 12, that is they given that pH value, but the cadmium hydroxide is a base. Okay, so to solve this problem, let us write the equilibrium of cadmium hydroxide. CdOH twice, that dissociates as cadmium plus 2 plus 2 OH minus ions. Okay, and KSP of KSP is this is cadmium hydroxide is AB2 type of electrolyte. AB2 type of electrolyte, KSP is 4S cube. 4S cube. Okay, in the problem they didn't give the solubility product. They didn't give the solubility product, but we have to calculate the solubility product. That's why I write this equation, KSP is equal to 4S cube. So for solubility product for AB2 type of electrolyte is 4S cube. So 4 into, they gave that molar solubility of cadmium hydroxide, that is 1.8 into 10 power minus 15 whole cube. This becomes minus 15 and 1.8 whole cube into 4. Okay, that comes out to be 24.9 into 10 power minus 15 into 10 power minus 15. So KSP is molar solubility product is 24.9 into 10 to the power of minus 15. But they asked to calculate the expected solubility of cadmium hydroxide in a buffer solution of pH 2. In a buffer solution of pH 2. So actually cadmium hydroxide is a base, but they given that pH is equal to 12. So we have to convert that pH. They given that pH is 12. So POH is 2. POH is 2. If POH is 2, then concentration of OH minus ions is 10 power minus 2. Okay, 10 power minus 2. Okay, so KSP is equal to, let us write the solubility product, that is cadmium plus 2 into concentration of OH minus square. They asked to calculate the expected solubility of cadmium hydroxide. Cadmium hydroxide are Cd plus 2 ion concentration. The expected solubility of Cd plus 2 ion concentration. We can calculate Cd plus 2 concentration because we know the KSP, that is 24.9 into 10 to the power of minus 15 and Cd plus 2. And we know the concentration of OH minus ions. They give that pH and we convert the we can get the POH from pH 12. Okay, because pH plus POH is equal to 14. So we can get the concentration of OH minus ions. Concentration of OH minus ions is 10 power minus 2 whole square. So Cd plus 2 is equal to cadmium plus 2 is equal to concentration of cadmium plus 2 is equal to 24.9 into 10 to the power of minus 15 by 10 power minus 4. 10 power minus 4. So This is 24.9 into 10 to the power of minus 15 into 10 power 4, that is 24.9 into 10 to the power of minus 11. Okay, 10 to the power of minus 11. If you multiply with the 10 and divide with 10, 2.49 into 10 power minus 10. So, expected solubility of cadmium plus 2 is 2.49 into 10 to the power of minus 10. Right? Right. Next problem. Okay. Problem 4 is, this is very important problem. An aqueous solution contains an unknown concentration of Ba plus 2. When 50 ml of 1 molar solution of Na2SO4 is added, BaSO4 just begins to precipitate. The final volume is 500 ml. The solubility product of BaSO4 is 1 into 10 power minus 10. Then what is the original concentration? It is a long problem, but we have to understand the problem first. Okay. An aqueous solution contains an unknown concentration of Ba plus 2. So, let us take the unknown concentration of Ba plus 2. Ba plus 2. Okay, when 50 ml of 1 molar solution of Na2SO4 is added, when 50 ml of Na2SO4, 50 ml of 1 molar Na2SO4 is added, BaSO4, I think it is barium sulfate. Barium sulfate just begins to precipitate. When 50 ml of 1 molar Na2SO4 is added, the final volume is 500 ml. So, when 50 ml is added, the total volume becomes 500 ml. That is, how much volume of barium plus 2 is present here? 450 ml. So, it is 450 ml, because after adding 50 ml, final volume of the solution is 500. Then, so 450 ml of barium sulfate is there. So, to that 50 ml of 1 molar Na2SO4 is there. So, we know the 50 ml Na2SO4 concentration, but we do not know the barium plus 2 concentration. So, then we can calculate the barium sulfate concentration by using the formula M1V1 is equal to M2V2. M1 is the barium sulfate concentration, M1, and its volume is 450 and the final volume is its concentration is 1 and its volume is 50. Okay, so sorry, this volume, when 50 ml is added, this total volume becomes 500. Total volume becomes 500 ml. So, we should take the 500 ml here, right. So, M1 is equal to 50 by 500, that is 1 by 10, that is 0.1. So, 500 ml of barium sulfate concentration is 0.1 after adding 50 ml of Na2SO4. After adding 50 ml of 1 molar Na2SO4, this total volume of the solution becomes 500 and its concentration is 0.1 molar. Okay, when Na2SO4 is added, barium sulfate just begins to precipitate. Okay, already I told you in the earlier video, last video, if ionic product is greater than solubility product, precipitation takes place. If ionic product is less than solubility product, no precipitation takes place. If ionic product is equal to solubility product, that is the case where salt just starts precipitation. So, this is the case. This is the case. In this case, that salt starts precipitation, then condition is ionic product is equal to solubility product. Ionic product is equal to solubility product. So, they gave that solubility product. What is that solubility product? 1 into 10 power minus 10. Ionic product is barium. The ionic product Ba plus 2, concentration of ionic product is Ba plus 2 and concentration of SO4 minus 2. Concentration of SO4 minus 2. So, we know the concentration of Ba plus 2, that is concentration of Ba plus 2 is 0.1 is into concentration of SO4 minus 2. Okay, SO4 minus 2 is okay. So, when we add okay, sorry, when we add barium sulfate solution and Na2SO4 solution, there is a common ion is SO4 minus 2. So, concentration, this concentration is SO4 minus ion concentration. So, the concentration of SO4 minus is 0.1 and concentration of Ba plus 2 is equal to 1 into 10 power minus 10. So, concentration of Ba plus 2 is 1 into 10 power minus 9. So, concentration of barium plus 2 concentration is 1 into 10 power minus 9. Okay. But they asked to calculate the solubility product of barium sulfate is 1 in 10 power minus 10, and what is the original concentration of, what is the original concentration of, what is the original concentration and what is the original concentration, okay, in which SO4 minus 2 concentration is 0.1, but they asked to calculate the original concentration. So, initial volume is 450. So, we know the original volume from the what is the original concentration. So, we can calculate the formula by using the formula M1V1 is equal to M2V2. M1V1 is equal to M2V2. Okay. So, M1 is molarity, that is the original concentration M1, and original volume, initial volume is 450 ml, already I told you this is the 450 ml, and M2 is M2 is 0.1, M2 is M2 is what is the M2 concentration is barium plus 2, and after adding Na2SO4, the final concentration of Ba plus 2 is 1 into 10 power minus 9, 1 into 10 power minus 9, and its volume is 500 ml. Okay. So, M1 is equal to 1 into 10 power minus 9 into 500 by 450, which comes out to be 1.1 into 10 power minus 9, 1.1 into 10 power minus 9. Okay. So, concentration, initial concentration of barium plus 2 is 1.1 into 10 power minus 9. Okay. So, this is very important, okay, to understand. From this problem we can understand the things are happens like this, right. So, we should keep this problem in our mind. So, this problem enables to think like that, enables us to think like that whenever this type of problem is given. Okay. Problem 5 is, will a precipitate of magnesium hydroxide be formed in a 0.001 molar solution of MgNO3, and if the pH of a solution is adjusted to 9, Ksp of MgOH twice is 8.9 into 10 power minus 12. Okay. So, they asked that whether will a precipitate of MgOH twice is formed or not when these conditions, in these conditions. Okay. So, MgOH twice, they gave that here will a precipitate of MgOH twice is be formed in 0.001 molar solution of MgNO3. So, the solution is MgNO3 and it is present in pH of 9. Okay, but MgOH twice is a magnesium hydroxide is a base, but MgNO3 will MgOH twice, magnesium hydroxide is a base, but given pH is 9. So, pH they gave that the pH is equal to 9. So, from this pOH is 5. So, concentration of OH minus ions is 10 power minus 5. Concentration of OH minus ions is 10 power minus 5. So, concentration of OH minus ions is 10 power minus 9, but MgNO3 solution is present in sodium hydroxide solution of concentration 10 power minus 5. In such case only MgOH twice is formed. In which condition magnesium hydroxide is formed? If MgNO3 is in the solution of concentration of OH minus ions 10 power minus 15, then this OH minus ions forms the precipitate with Mg, then MgOH twice is formed. So, OH minus ion concentration is 10 power minus 5. So, in this solution 10 power minus 5. So, MgOH twice. So, Ksp is equal to concentration of Mg plus 2 plus concentration of OH minus square. Okay. So, concentration of Mg plus is concentration of Mg plus is 0.001 and concentration of OH minus is 10 power minus 5 whole square. Okay. So, solubility product is 8.9 into 10 power minus 12. Okay. So, which comes out to be this is 10 power minus 3 and this is 10 power minus 10. So, this is 10 power minus 13. This is 10 power minus 13 and solubility product is 8.9 into 10 power minus 12. So, here this is the ionic product 10 power minus 13 and this is the solubility product. When will precipitate form? When ionic product is greater than solubility product, then in such case precipitation takes place. But here the ionic product is 10 power minus 13 and the solubility product is 8.9 into 10 to the power of minus 12. So, in this case ionic product is 10 power minus 13 and the solubility product is 10 power minus 12. So, solubility product is greater than. Okay. So, in this case MgOH twice precipitation will not takes place. So, no precipitation takes place under these conditions. Okay. So, these are the problems by which we can understand the more complicated problems. I hope these problems will help you to solve more complicated problems in your preparation. Thank you for watching.